For this problem, we'll explain how the apparatus for Jaeger's blowing bubbles method works in further detail, and go through some descriptive physics. As you can see, we have the bent glass manometer tube with water inside of it. This arrow here represents the constant pressure P0 you'll be providing from the syringe, and lastly the capillary tube here submerged in methanol solution. I will also note that the natural atmospheric pressure I've named P subscript A. So first of all, let's assume that the constant pressure we are applying is greater than atmospheric pressure. What this does is it helps us define a direction for some equations, and it is a reasonable assumption. For our first equation, we will say that since P0 is greater than atmospheric pressure, it must be the sum of atmospheric pressure and the difference between the two pressures, or delta P subscript 1. Our manometer helps us to measure this change in pressure. Our second equation goes the opposite direction through the capillary tube. We are given that there is a known change in pressure between a bubble and a liquid called a Laplace pressure, delta P subscript 2, as well as a change in pressure due to being submerged beneath a depth of water, delta P subscript 3. The constant pressure we apply stores itself temporarily in the gravitational potential of liquids and gases, and the surface tension of a bubble. By adding these two equations and seeing that atmospheric pressure cancels on both sides of the equation, we are left with a pressure equation that is independent of the room pressure and the pressure that we apply with the syringe. For this lab, I also recommend reading over graphing hints at the beginning of the lab manual, specifically the example that shows how to graph 5 versus time. Also, the relative number of methanol molecules sample calculation that is at the end of this lab.